These data streams represent a new baseline in software engineering. Over the last 2 years, developers have integrated AI agents into their standard workflow to manage the increasing complexity of modern code bases. This reliance on AI creates an immediate architectural trap: vendor lock-in. Adopting tools like GitHub Copilot or Claude Code means tethering your entire development pipeline to a single provider's proprietary ecosystem. That dependency introduces operational friction. Scaling these tools requires accepting opaque pricing models and unpredictable API costs that can fluctuate across hundreds of individual seats. For an enterprise, the most significant risk is data privacy. You are actively routing proprietary logic through external corporate servers, often with zero clarity on how that logic is indexed or stored. Trading architectural data sovereignty for short-term productivity gains creates a long-term liability. When the code is the product, surrendering control over the development environment is a dangerous compromise. OpenCode.ai was built to address this specific friction. Since its launch, the project has reached over 160,000 GitHub stars and supports 7.5 million active monthly developers. This adoption rate reflects a widespread rejection of proprietary silos. Developers are moving away from closed environments in favor of transparent, community-driven tools. OpenCode shifts the industry from locked ecosystems toward a model-agnostic, protocol-based foundation. It replaces the corporate black box with a modular hub. This framework decouples the developer's integrated development environment from the underlying AI provider. It allows the editor to function independently of the model being used. Standardizing these underlying protocols ensures that an engineering team retains its independence, even as the landscape of AI providers continues to shift. Accurate AI code generation requires more than a simple text read of the current file. It requires deep, interconnected context about the entire application structure. OpenCode achieves this through Layer 1 of its architecture: integration with the Language Server Protocol, or LSP. The LSP provides the same signals an IDE uses for autocomplete and error highlighting. OpenCode feeds these compiled signals, like definitions and references, directly into the AI model. These resolved references transform the AI from a text predictor into a semantic pair programmer. The model doesn't just see strings, it sees the logic and dependencies of the codebase. By standardizing contextual understanding at the protocol level, the system eliminates the need for proprietary context-gathering tools. Once the AI has the context, it needs a standardized way to communicate with the developer's workspace. This is Layer 2. This diagram shows the Agent Client Protocol, or ACP. It unifies communication across different editors, allowing the same AI intelligence to work seamlessly in VS Code, JetBrains, or NeoVim. To extend this capability, the architecture integrates the Model Context Protocol, or MCP server. The MCP server allows the AI agent to reach outside the editor. It can securely query external databases, check CI/CD pipelines, or pull data from issue trackers to inform its suggestions. This capability comes with a specific engineering trade-off. While MCP integration expands what the AI can do, it mathematically increases the context payload and the resulting token overhead. Standardizing these communication layers future-proofs the engineering toolkit. It ensures that the AI can interact with the entire dev stack, regardless of which individual tools are swapped out. AI context windows are linear and finite. This creates a bottleneck during long coding sessions, where the model forgets the earliest parts of the conversation. Layer 3 of the OpenCode architecture solves this through an algorithmic mechanism called auto-compact. The system monitors token usage in real time. When it mathematically detects that usage has reached 95% of the model's maximum capacity, it triggers a summary event. The system compresses the conversational state into a summary and immediately initiates a fresh session with that preserved context. Handling memory degradation algorithmically allows for parallel multi-session workflows that match the way human engineers actually work across multiple files and features. Layer 4 is the apex of the architecture. By standardizing the lower layers, the system achieves absolute model neutrality across more than 75 different providers. This creates a direct economic advantage. Developers can route routine, high-volume planning queries to ultra-fast, low-cost models. When deep debugging is required, the system can instantly hot swap the output path to a premium, high-reasoning model. This swap occurs seamlessly within the same session. All LSP context and conversational history are preserved, even as the underlying intelligence changes. Dynamic routing gives the economic leverage back to the engineering team. It forces providers to compete on performance rather than ecosystem lock-in. The ultimate test for any AI deployment is whether it can maintain state-of-the-art capability in a completely offline, air-gapped environment. For a mid-sized financial institution, strict data compliance often makes external AI tools impossible to deploy. Their code cannot leave the local network. OpenCode solves this by operating locally. Engineering teams can deploy the entire stack on-premise, using local inference tools like Ollama to run high-performance models without an internet connection. This architecture provides a technical guarantee: zero central data ingestion and zero external API pings. True air-gapped capability is the prerequisite for AI adoption in high-security sectors like healthcare, finance, and defense. Effective enterprise deployment also requires auditable collaboration across engineering teams. OpenCode provides granular session controls. Sharing can be manual, automated, or entirely disabled via configuration to protect sensitive intellectual property. By unifying context, communication, memory, and model selection all together, OpenCode establishes a standardized infrastructure for the modern engineering stack. This reflects a broader shift in software development. The relationship between the developer and the machine is moving from rented products toward owned protocols. The future of enterprise engineering belongs to organizations that maintain control over their foundational infrastructure. Independence is not a feature, it is a prerequisite. These days